Hey everyone, I'm back with another lecture video. This one's lesson 9, chapter 12, about rocks and mineral resources. We're going to continue our look at Earth's resources. This chapter will be on, as it says, mineral and rock, and the next chapter will be on our energy resources. So, as we're talking in this lesson, we're going to be talking about mining and stuff a lot here. But keep in mind, since we are in Kentucky, we think about mining as coal mining. And I'm not going to mention that in this lesson because we're going to talk about the energy resources in the next chapter, and that's where coal will fall in. So when we're talking about mining in this lesson here, it's going to apply the same practices and the same processes that we talk about are going to apply to those coal mines as well. But we're just not going to mention coal until the next chapter. So as we get into this, we need to think back to our previous chapters early in the semester when we talked about the different rock types and how rocks are formed and what minerals are and how they're structured. We studied that already, so we should already have a good background on that formation and what it means. And we're going to just kind of add to that as we get into this chapter. You see this photo here. This is just kind of an introductory photo of a highlight mine, basically salt. This is a sedimentary salt mine that's probably located, if I had to guess, out in the American West, probably in the Utah area. I'm not sure exactly. It doesn't say exactly where this one is. When we start talking about these minerals, of course, I just alluded to, these can exist in any of the types of rocks that we studied. Remember, we have igneous, metamorphic, and sedimentary rocks. And we can extract specific types of minerals from each of those rock types, and we do that. The way we extract those varies greatly depending on where they're located, what they are, what type of rock it is, etc. This is just talking about, I know when I was in geology in college, we never used a left-hand column, which is the Knoop hardness scale. We used the Mohs it says at the bottom here, the Mohs hardness scale. This is a hardness scale of some of your minerals. And what that means is just what it sounds like. How hard are these minerals? How hard is it to crack or break these minerals compared to other things? So you see it starts at 0 and it kind of trends up, and you see diamond is by far the hardest mineral that we have. And diamond is an interesting mineral because it's just straight carbon. It's one element. It's carbon. Graphite is also just carbon. They're made out of exactly the same material. They're just organized differently, structurally speaking. Those carbon atoms were deposited or formed in a way that was a little bit different in the two different environments in which they were formed, so they have very different properties. And if you're wondering what graphite is carbon. It's very light. If you think, I don't know if anybody uses their old school pencils anymore where you have to sharpen them, the pencil lead is graphite. It's kind of a platey type structure. It shears off really easily, and that's why pencil leads, when you write, they leave behind that carbon on the paper. So that's where we got pencils. We also have carbon fiber. That's the same kind of stuff. Same material. It's processed differently, and we use that in a lot of things. Think about tennis rackets, or there's all kinds of stuff we use that in. So here is a table that talks about the annual per capita consumption rates of different mineral resources. So what does that mean? Probably doesn't mean much to you reading that for the first time. So anything we talk about, and we talk about per capita, that means how much of this material does each one of us use on average every year. So you might look at this sheet, and you can say, okay, so it says sand, gravel, and crushed stone. And the average person in the United States uses 16,000 pounds of this a year. You might think, okay, well, I've used none of that. That's not what that means. It doesn't mean you personally. It means if you take all the people in the United States and then you take the total pounds or tons of that material that we use, you divide it by the number of people, that's the average of what we use per person. So this breaks down to, in the United States, we used 6,194 pounds of gravel, sand, or crushed stone per person. That's how much we use. So your footprint by living in the United States is that much of that material. Cement, you can see second there with 655 pounds per person. These are all non-metals. When you get down to the metals, you can see on the most part they're less than the non-metals, but still quite a bit of metals. And this is just, again, this is a graphic, an aid to let you know how much of this stuff we actually use in the year for our population here. And it's pretty extraordinary how much do we actually do use. So when we're talking about minerals and deposits of these minerals that we're going to use, we have to rate these and look at, okay, are these things that we can use, and is it economically feasible for us to use these? So the first thing we have to do is we have to have geologists, and again, we're looking at environmental geology this semester. So environmental geologists really look at how this stuff interacts with the human population and how we get it out of the ground impacts the earth. What a different type of geologist might do, let's say that they're a petroleum geologist, or they're an expert in a certain field of metal, say iron, they're going to find the ore deposits, the ore resources on the planet. And they're going to look at those. And they're going to say, okay, is this a big enough deposit? Is it pure enough to be economically feasible for us to mine this? And the answer might be no today, but it might be yes 10 years from now. Because as our population grows and we need more of that material and we're running out of it in other places, what might not be economically feasible today to mine, we might need that in years to come. It's pretty surprising when you look at how much of the resources that we use every day and how much that they speculate that we might have left on the planet. Some of it is going to run out sooner than later. And while most of us personally don't think about that in our everyday lives, there's going to be a point in time where we're going to be forced to think about it. And typically, when that point in time comes, it's already too late. And that's just the nature of humanity. We always want to push stuff off until it's too late to do anything about it. So that's what we're going to talk about right here. So you have ore deposits. You can look at that as a resource. And then you have reserves, which means reserves are economically feasible typically to be mined. Now, they do classify reserves. Sometimes they'll say they're sub-economic. And that means they're there. They're probably there in a quantity that could be mined, but it's probably a little bit too expensive to do it right now. Whereas a deposit or a resource, we know it's there, but we're really not going to mess with it right now. That's the best way to put it in really simple terms. And this chart right here kind of goes over that. So we've got identified deposits. So that means some type of geologist has identified that we have this type of mineral at this location. That's what that means. And then you have the economic ones that we can mine these right now. We're going to make money on that. That's a reserve. And then you have, it's kind of borderline. We could mine this right now and probably make money on it, but probably not much money. That's going to be a marginal reserve. That's the ones that they're going to put like on the list and not do right now, but they have it in their back pocket if we really need this in the next few years. And then sub-economic means that they don't think that's going to make enough money to even mess with right now. So then you jump over to these columns and you see they both start with undiscovered. So that means the geologists speculate that they're there, or they think they're there, but they haven't really tested yet to know that they're really there. And what differentiates these two columns is first of all, you see they're called resources instead of reserves. Okay, so reserves have been identified. If they haven't been identified for sure, they're called resources. In this column, it's called a hypothetical resource. This column is called a speculative resource. The difference is these are undiscovered in areas that we've already done some mining and we know that material is there. So we've already mined some of it in this area, and the geologist thinks, okay, we've already discovered it's in this area, so we think that there's this much more, that there's X number of tons left there. That's kind of what that means. So hypothetical, think of back in our first chapter, we talked about a hypothesis. We talked about what that means. It's an educated guess based on several criteria. So they're saying, okay, we know the stuff is in this area, and we hypothesize that there's this much more potentially here. That's what a hypothetical resource is. A speculative resource is more of a broad, okay, we know this is a convergent plate boundary, and we know that this type of mineral forms in these types of areas, so we're pretty sure that we're going to find more. Let's say we're looking for gold. We're going to find more gold there, but we really don't know how much, and we really don't know where it's at. But we're pretty sure we're going to find some somewhere. That's kind of an example I can give you what speculative is. They're using their scientific knowledge, but they haven't actually put feet on the ground, or they don't actually know it's there. So I hope that kind of somewhat clears those words up for you when you're trying to determine which of these is which. So I'm not going to go into great detail on these things that are in your textbook about the process of the diamond pipes. Just remember that the diamonds, we talked about the hardness earlier, diamonds are formed at depth. They're formed down in the upper mantle, way underground, and geologic forces over geologic time move those to the surface. And then you have these areas called diamond pipes where these things get exposed to the surface. And that's where humans can actually access these and mine these. So they're not formed near the surface. They're formed way deep underground. And then geologic processes lift these up to the surface. And then through weathering and other things, humans discover these, they found out they're there, and then they start mining and digging. So keep in mind too, when we start talking about the mining of these minerals, probably the very first time that humans started using minerals from the planet was very simple. They found stuff on the surface. They found out they could use it in some capacity. And then over time, as humans developed and evolved and got smarter, they realized, okay, if it's on the surface, there's probably more underground, so let's dig down a little bit and see if we can find some more. And that's kind of the simpleton's version of how this probably got started. And then eventually you have people digging very deep mines to get at this stuff that they've discovered initially on the surface. So again, it talks about the intrusive deposits, the layer deposits, the hydrothermal. This is all in your textbook. We have limited time on these lectures, so I'm not going to get into that real deeply. The intrusive deposits means that magma has come up near the surface. It's got into some of these veins, these faults, these cracks, whatever the case, whatever they are, and it's depositing these minerals in there in some capacity. You see the layering down here? That is all based on how the magma cools. If you have a very slow cooling magma, you get cooling at a rate that certain reconstruction of these elements starts the cooling process, and you'll get different layers of kind of pure mineral because they fall out at different times in that cooling process. So you'll get one layer here, one on top of it, because they're cooling, and as it starts to cool, different minerals reform and restructure at a certain temperature. It's very similar, if you remember, to how we studied how different sediment size types, grains like sand and silt, move down a river and are dropped out at different speeds of water flow. The large ones drop out first, and then the smaller ones next, and it keeps going down. This is kind of similar to that idea. Now this is more of a heat chemical type structure. That's more physical, but it's the same idea in that you've got a hierarchy of how this is forming depending on the temperature. So that's why you see these striations. If you just looked at that and you don't know that much about geology, you would want to think first that was almost sedimentary rock because it forms in layers like that. But this is just how that rock formed at the bottom of these magma chambers as it started to cool. So again, you've got hydrothermal deposits. You can see here where you had rock existing, you had these small cracks and fissures in the rock. The magma was pushed up into these, and it cooled and restructured those atoms, those minerals in that rock. And now you've got veins, they call these veins of different types of minerals in this rock. Now these are relatively small here. You see that appears to be a pocket knife, so that's what, an inch wide there. That's probably 5 or 6 inches wide here. I mean, sometimes these things can be 20, 30, 40 feet. I mean, they can be really big too. So it's just not tiny all the time. It just depends on what the activity is like and how big these veins were. But that's an example of how it intrudes into this rock through these fissures. Sulfide deposits, it's covered in your textbook as well. We have a lot of sulfides that leave the ocean vents at divergent plate boundaries. Think in the middle of the Atlantic Ocean. There are certain minerals that will precipitate out within these sulfides, and that's where we get a lot of our minerals like that. Now remember that we do ocean mining, but it's not that prevalent, and especially at those depths, and we're talking about the middle of Atlantic. But remember that over geologic time, over the millions and billions of years, the plates have moved around. So you have areas that were once at a divergent boundary on the ocean floor that was spreading apart. At one time they were down there, but now they might be up on the side of a mountain somewhere. They might have been uplifted to the edge of a continent. And that's where we're going to find these reserves. They're ancient, they're very old, but they're still there. So keep that in mind. That's something that they do discuss in the textbook as well. So metamorphic processes, and what I found in teaching my students is sometimes it's hard to determine because we talk about how the metamorphic process worked earlier in our earlier chapters, and for people that are new to geology, sometimes it gets a little confusing because you've got igneous rocks that form from magma primarily, and then you've got metamorphic processes in which magma comes up and heats rocks, and you got magma, some effects from the magma there. So what exactly is the difference? And just to review, an igneous rock is formed from magma that's in its basic elemental form as it comes up through the mantle. So it's original. A metamorphic rock is influenced by magma in that there's existing rock there. The magma has moved back close to that for some reason, and it's either cooking or baking that rock and kind of restructuring the atoms within those minerals in that rock and changing the characteristics of it. Or there's such intense pressure on that rock. Say if there's some uplift happening near the plate boundary, you've got layers of rock that get kind of twisted and contorted, and that pressure can also cause them to change, rearrange their crystalline structure. So that's what a metamorphic rock is. It's a previously existing rock that is subjected to the heat and or pressure. And that's what these two different types of metamorphism are. Regional is typically going to apply more to your pressure type movements. Contact's going to be from that magma being close and kind of baking that rock. And here's a good visual on this. As you can see here, this magma dome has come up into these rock layers, and what it's showing you is, so if this thing went back down right now and cooled, this would all be igneous rock in the middle. But you see these shaded parts on the outside, it's so hot around this magma dome that those existing rock layers that it intruded into right there actually kind of baked and reorganized structurally within their layers. That's where the metamorphic rock would be found, around that. So that's a very good graphic for you to remember about where those metamorphic rocks are forming versus igneous. Now you might have some igneous veins going up because this magma is actually getting up into these cracks. Like I said, these might be vents, there might be faults, whatever these are here for. If magma gets up in there, you might have a bunch of metamorphic rock with a vein of igneous rock going through the middle of it. So keep that in mind. And here's just a cross section of a mountain where you can see some of the effects of this metamorphism happening. I wanted to point out on this slide too, before we move on, a very common type of metamorphic rock is slate. And slate comes from shale. We have a lot of shale around here. If you remember, shale was a sedimentary rock, and it's sort of like a mudstone almost. The grains on it are similar to mud, but it's in very thin layers. You can break it really easily. We have shale layers around here. You can see them around lakes sometimes, and you can really break it up easily. It's really a kind of a ratty little soft rock. It doesn't hold together very good. It breaks really easily. Sometimes if it gets really wet, it actually gets really soft. I mean, it almost melts sometimes, depending on the type. But when it gets exposed to heat and pressure, it turns into shale. And that is it's a platy rock. It's in those layers, but it gets really hard. And you can break it, but it's hard enough that it keeps its structure really well. And that's, back in the old days, that was the primary use that they used, was shingles for roofs. Now it's too expensive, and we have asphalt shingles that are a lot cheaper, but shale used to be a very useful metamorphic rock for roofing. So other sedimentary processes that gives us minerals, you have, I'm going to kind of jump over the placer deposits. We're going to kind of go through these one by one in the next few slides. But sedimentary processes, sometimes we don't think of these as much, but we actually get a lot of our minerals from sedimentary processes. So placer deposits, you read in your book, placer deposits are ores or resources that we have of these minerals. I'm just going to use an example because I think I can explain it better with an example. We think about gold. If any of you ever watched any of the gold rush shows on the Discovery Channel, whatever channel they're on, some of those guys are in the creeks and streams looking for gold. So when they find a bunch of gold on the bottom of the stream, maybe in a big hole down here, that's a placer deposit. And what's happened is somewhere up in one of these valleys, in this case it's right here, a gold vein was exposed to the side of the valley. And it weathered, and it eroded down and fell in the stream. And we've talked about erosion in previous chapters, how it can carry sediment down a stream and it washes it downstream. Because gold is really heavy as an element, it will fall out and it will stay in pockets, the deepest pockets in the river. Most of these rivers, it doesn't show down here, are in mountains, and they're very steep, and it's whitewater. I mean, just waterfalls. So the gold will really settle in these pockets of little still spots or under a waterfall where it's kind of deep, and they can kind of sit down on the bottom and not be disturbed once they hit the bottom. So these guys go looking for these placer deposits, which are just deposits that have eroded from this area up here and gone down river, and now there might be a big area down here that's full of gold pieces from that original deposit. That's what a placer deposit is. It doesn't have to be gold. It can be any other mineral that washes down due to erosion and gets deposited somewhere else downstream. And some of these might be really old. I mean, might have been deposited millions of years ago, and we are digging them up. They might not be in an active stream even. They could be up here on the hillside from when this valley was higher, and we find these placer deposits on the hillside. So we also talk about mining and the processing of minerals in this chapter, and we're kind of jump back and forth between some of these different topics here on the next few slides. So we have surface mining, we have underground mining, we've got placer mining like I just went over. I've already talked about that one. Asbestos, there's a case study in your textbook. I encourage you to read that. We'll have a question on that most likely on our test for this module. Asbestos was a big deal throughout the 1900s. When I started with EPA, it was a really big deal because it was being removed from a lot of places like schools and any government buildings. Asbestos, if it's contained and it's not disturbed, it does not harm humans that much because it's made from these. This is a microscopic image. It has a lot of very fine little sharp particles in it. It's a naturally occurring mineral, and it has great properties. You can see here, this was a suit made of asbestos. You could walk through fire. It's very insulating. It will not conduct heat or cold whatsoever. And that made it very popular back throughout the 18 and 1900s, even before that. I mean, even going back to Roman times, there were some evidence that they used asbestos in things. The problem is, though, if it's not contained, which means it's not in some kind of stable encapsulated form, if this stuff is broken up, it gets into the air. These individual little slivers get into the air very easily, and if you ingest those or breathe those, your lungs will take those in, and your lungs cannot get rid of them because they don't break down at all chemically. Due to the shape and the sharp edges, you can't expel them. And there are a couple of diseases, asbestosis and mesothelioma is the cancerous form of that. A lot of people died from that. So there was a big push in the 1980s and 1990s to get rid of a lot of this stuff. It was kind of controversial because the government decided to remove all of it from government buildings, like I said, like schools and stuff. There were arguments made that, okay, we're causing more problems because we're actually disturbing it more, but they decided it was better to get it out. I'm not letting one right or another on that. I just know human behavior, and through my career, it's probably better to go ahead and get it out of the way, because somebody's going to inevitably disturb that stuff. And it is very, very carcinogen. It causes cancer very easily if you do ingest that. So that's the case study on asbestos in your textbook. We have some deposits of minerals that are formed through weathering. And if you remember in our last chapter, there's a very good example of this. It's different, totally different thing, but it's the same principle. Remember the soil horizons that we studied. And remember how as water leaches down through those soil horizons, it kind of leaches out certain minerals and chemicals and takes them down deeper and forms a different horizon. This is the same principle. So if you had a vein, a hydrothermal vein that had different minerals in it, and it weathers over time, the water will eventually infiltrate down through this rock. It can dissolve out certain minerals, and when it gets to the water table down here, there's actually typically two zones of mineralization. There's one just above the water table and one just below it. And that can be an ore deposit of certain mineral depending on what that water is leaching through in this hydrothermal vent. So same principle of soil horizons, but different chemical processes going on. Evaporite deposits are sedimentary in nature. They're typically formed when you have an ocean, a shallow sea, or a lake that eventually dries up. The water leaves and evaporates, but it leaves behind all the salts and chemicals in that seawater or fresh water at times, more seawater. These are major evaporite deposits in the United States. You can see we have a slight one here in South Central Kentucky. It's just north of Bowling Green area, actually. Not very major at all, so it's not anything that it's very striking or talked about very much. We typically see more mines in this stuff out in the west out here, and Michigan has quite a few of these. This chart over here, this pie chart, is just the basic. This is the average of what types of salts are in seawater. So this is what you could mine out of these. Typically, we're talking about salt, and sometimes gypsum are the two most primary ones that we talk about. This is just a graphic on what we just mentioned. Here's the one in Michigan that I mentioned, all in your textbook. You can take a look at that. This is an evaporite deposit out in Utah. I'm pretty sure this one is in Utah. This is actually it on the surface right here where a lake has dried up and the salts are left behind. So now we're getting into the mining techniques. This photo is a good example. This is a hydrothermal vein that had some type of mineral. Probably, I think this one was gold, maybe. Somebody found a little gold in here. So, like 1880s, what'd you do? You would just start digging this out. So you start digging this out, and you have to haul this rock off somewhere. So they took it up on top of the hill here and dumped it up here. So that's a very primitive mine, and that's kind of how mining started. You find something on the surface, okay, it's on the surface, it's probably underground, we see this vein, let's start digging and see what we can find. So you can see just in this picture what kind of problems that this could cause, just even if in its primitive form. First of all, you've dug out this whole hillside, you've got buildings below it. This is obviously a drier climate, but if they were to get a big rainfall, all the water up here is going to run right down this and right down here. There looks like there's a drain coming out of it right there. You're going to have some severe erosion coming down there, and it possibly endanger some of these buildings down here. Also, you have the tailings up here. So oftentimes, what we've got to remember is, if you remember early on, I said that nature moves toward an equilibrium. So it wants to stabilize itself. So a lot of these chemicals that we find in the ground, they're kind of been locked away. They're in their rock layers, and they've stabilized. So they're not really hurting much, even though they might be harmful to humans if we ingest them or breathe them or drink them or whatever the case. But they're kind of inert while they're in the ground where they were originally. Once we start messing with nature and we start digging this stuff up and piling it up here, now we've exposed it to the elements. Now the air is hitting it, you've got more rainfall hitting it, you've got percolation going through it, and now we might have runoff of some bad stuff that might be in these rock layers running off down the hill. So that's why mining can be such a bad endeavor. We have to have mining. I mean, in our everyday lives, we use almost everything we use comes from the earth, so we have to extract it. But the big question is always going to be is how do we do it safely and responsibly? And as you know, when humans first start doing things back in the old days, probably environmental concerns were not at the top of their list. So even from mines that were done 100 years ago or more, maybe 200 years ago, we still have pollution coming from those mining sites just because we disturbed it back then. So now, as we've evolved in time and we're capable, we have more technology, more energy, more machinery, we've graduated to bigger time mining. Open pit mining is one of the largest types of mining. I mean, you can see these holes that they dig underground are immense. I mean, just huge. And they're pretty destructive to the environment. They obviously ruin the ecosystem in that immediate area right there. But they're not as bad, potentially, as some other types of mining, depending on what you're mining. There's always conditions and factors in these things. Are you exposing this ground? Is there something that's really bad chemically in this sediment? If there is, then it could be really bad because as you're going down, obviously you're getting closer to the water table. And obviously any rain that falls on this cannot escape these holes. So it's going to the groundwater probably quicker than it should. So that's one problem with these open pit mines. Now the small inset photo up here, this is some iron-rich sedimentary rock. Interesting story. You can read about this in your textbook. But most of the iron ore that we mine in the world is found in sedimentary rock, which a lot of people would assume it would be from igneous rock. but it's from sedimentary rock. And it's found, most of it was put down in sedimentary rock between 1.5 and 2.5 billion years ago. And it has a large, even though it's a mineral, there's a large component of life as to why we see it in this type of rock. You see the striations in this rock. The dark's going to be your iron ore, or I'm sorry, the red's going to be your iron ore because it's oxidized. The dark's going to be some other type of sediment. So why do I say that life had something to do with this? Because minerals are inorganic by definition. But what happened is, during that period of time, 1.5 to 2.5 billion years ago, is when life first started flourishing on this planet. Now remember, I'm saying life. That is the very basic life. Algae, things that use photosynthesis. That's when photosynthesis happens, we've discussed this earlier in the semester, that creates oxygen. The more oxygen that was pumped into our atmosphere at that time, there was iron ions in the water. I'm explaining this very basically for everyone. I'm certainly not a chemist, so I won't swear by all of this as far as how accurate I'm explaining it. But essentially, there was a lot of iron ions in the water at that time. The more oxygen that was placed into the atmosphere, thus in that water, caused the iron to fall, basically precipitate out of the water in that shallow water, and it accumulated in layers on the bottom of that water body. And that's where we get, that type of rock is basically where we get most of our iron ore from today. Strip mines, we'll talk about this more in detail when we talk about coal in the next chapter. Strip mines are another type of mining that we use for coal a lot and other minerals as well. Very destructive to the environment. You can see the big pieces of equipment there, and you can look around. That whole area is just a moonscape. I mean, there's nothing there. You're basically just stripping off the upper part of the earth anywhere you're doing strip mining, and you're devastating the environment. Depending on what you're mining, you can see that stuff is falling off this conveyor belt right here. I'm not sure exactly what type of mine that is. I don't recall from the textbook. So they're going to process this, whatever it is, and they're going to have waste material, the tailings from that. Depending on what it is, what the chemical composition is, you might have runoff from those tailings on that. Underground mining was probably one of the first types of mining after just digging on the surface, the primitive ways. Humans started digging holes deeper and deeper to reach deeper and deeper deposits. You can see here how they will reach deeper deposit horizontally or diagonally here. It's kind of almost vertical, just hitting this deposit here in different locations. This is common in South Africa in one of their gold mines that I know that's really, really deep. It's deep enough that they're getting close enough. It's like, if I remember correctly, I think it's like 13,000 feet deep. It's like 140 degrees down there because they've passed the zone of where you would typically think it would be cooler underground, and they're getting to the zone where the earth is heating up from the mantle because of the heat from the magma way down deep. So it's ridiculous how deep that mine is, but that's an example of a mine. So underground mining with technology today, the strip mines, the open pit mines are a little bit easier to do with the heavy equipment, and they're much safer for human beings because, as you know from stories you probably heard from Eastern Kentucky and the coal mines, this is very dangerous to put humans underground in mines that have been dug. There's problems with cave-ins, with gases. It's just a very dangerous endeavor, and it's very labor-intensive to get stuff out of these mines. So this is declining, although there's still plenty of underground mines in the world today. The other types have gained more popularity. Hydraulic mining, I hope there's none of this going on in the world today. I'm sure in some developing countries they're probably doing this. this was so bad for the environment, they even outlawed this back in the 1880s in California. Um, this got popular with the gold rush back in the mid 1800s out west, primarily in California. And as you can see, they would dig a big hole where they thought there was gold. They would bring high pressure water in there, water hoses basically, and just start washing away sediment off the sides of these holes, and just creating just gigantic holes and tremendous erosion issues in these valleys, just washing it all down here. It was, you can see the people standing here. It was just a disaster environmentally. They outlawed that, I think, in the 1880s. And that should tell you how bad it was if they were thinking about the environment even back in the 1880s. So, okay, so we've talked about how they get these minerals out of the earth. So what do they do with it once they get it out? Very few minerals that we mine come out in a pure form. I mean, sometimes you might find a vein of gold that's pretty pure, but on the most part, you're not going to go in and find any minerals that are just, hey, look, I found a hunk of this and it's just a pure whatever it is. So there's ways that you have to extract that mineral from the other minerals around it or encasing it, or it's contained in it, whatever the case. So those are physical separation, and you can take a physical separation as our non-metal minerals such as rock, sand, gravel, all that stuff. You can actually crush it, break it up, screen it for separate sizes. That would be physical separation. Smelting is when you do have most likely some type of metal that's included in another type of mineral. You're going to melt that. You're going to physically melt it to the point that it separates the different minerals from each other, and you're just going to take that metal away that you're trying to get out. And then leaching is more chemical. So you take a big bunch of this material that you've removed, and if there's something specific in there that you're trying to get out, some chemical might be able to leach that out. Now that might be water. Sometimes some things you can leach them with water. Sometimes it's some type of acid that they run through it. So now we start talking about acid, like with copper. Now you start thinking, okay, well that's probably not going to be very good for the environment either, because when you start taking large quantities of stuff, putting large quantities of acid in there, there's going to be a mess somewhere. So here is just a general dot diagram of where the biggest copper deposits in the world are. And if you look at this and remember our plate tectonics map, you can kind of see where copper is formed. Typically around convergent plate boundaries is the most you're going to see. Now sometimes you'll see odd ones here and there, not around those type of plate boundaries. Those might be ancient plate boundaries, millions or billions of years ago, that are no longer functioning, but at one time they were. So sometimes we'll stumble across something like that. Copper deposits, again, this is a chart of all minerals that we import as a country, United States. The green ones are those strategic ones it mentions in your textbook. Strategic mineral deposits are ones that are very critical to our defense as a country. Yet you see two of these up here, we import all of them. We don't have any mines here that produce these, manganese and rare earth metals. We import 100% of what we use. Down here we have a few more. We're importing 73 and 71% of these, platinum and chromium. Cobalt as well, 61%. So what does that mean? That means if somehow we had a big world war tomorrow and all trade got cut off in the world, we're going to be without these minerals in the United States until we find a way to mine them or find some deposits here. But you can see there's a lot of minerals here that we import the majority. It's not down till here that we get below 50%. And you can see how small of a list that is, that we import less than 50% of these. So that's just a snapshot of, this was from 2018. I doubt if it's changed a lot since then. But so, supply of mineral resources. This is where we're going to start talking about what do we have out there, what are we going to need in the future, can we recycle something, what's recycling versus reusing. Basically, it's all a moving target because we don't really know what we have out there and what we're going to need in 10, 15, 20, 30 years. Because the population keeps growing, our technology keeps changing. There's so many different factors that scientists can't really keep up and say, okay, we're going to need this much in 30 years. We really don't know. We can make guesses. We can have an hypothesis about stuff, but we really don't know. What we do know is there's a finite amount of this stuff out there. And already in some of these mineral resources that we're mining, stuff that 30 years ago was not economical to mine, now we're mining because all the most economical mines have been used out. There's no more mineral there. So we're having to move on to more difficult mining areas, more expensive areas to get this stuff. That's a big reason right now. You know, we all talk about the price of gas and oil. You know, there's still a lot of oil in the world, but it's getting less and less as time goes on. And we're relying on other countries more. We have reserves here in the United States, and you're going to hear from the different sides of the political spectrum, which should we drill more in the United States or not, and this and that. The bottom line is this stuff is going to run out at some point. The easy stuff that we can drill in the United States, we've already drilled. The stuff that we have left, it's going to cost more for us to get to it, to refine it. The stuff from Canada, the tar sands that we talk about and people are arguing about with the pipelines coming from Canada, that stuff is just dirty. The type of oil that is very low quality. It's going to take more money to refine it. It even takes more money to transport it in those pipelines because it's so thick. So what you don't get told about from the politicians about that stuff is what all goes into getting it ready for us to use. And even though it's close right here to the United States, a lot of it is going to be actually more expensive for us to refine and process and get ready for us to use than just importing it from another country. A country like Saudi Arabia that has plenty of oil still. However, they're not going to have that forever. So the whole idea of us trying to find renewable energy sources, it's not just, you know, what a lot of people around here call your hippie environmentalists trying to get us off these. They're going to be gone at some point in the near future. And I say near, I don't mean like next week, but I'm talking about in the next generation or two, we're going to have to find these anyway, so why not start doing it now? There's no reason not to. So, the world mineral production, this is a chart that's in your textbook. It's a little bit alarming when we look at some of the numbers. This is basically, and again, what I said before, you know, we can't really pinpoint this because we don't really know what technology is going to do, what the population is going to do, what countries are going to be more advanced in 20 years or stay how they are, whatever the case. But the far right-hand column is what you should look at. And what that far right-hand column says, that's the estimated life of the reserves that we are pretty sure we know about right now. How many years of that do we have left as far as being able to mine this stuff? Now, 113 years of iron ore sounds like a lot. Your lifetime, my lifetime are going to be gone by the time 113 years comes around. But if you think about how short of a time humanity has been industrialized and realize that we're going to run out of iron ore in 113 years, that's pretty quick on the geologic scale especially. Then you look down the list and you look down here at copper, that's 40 years. We use a lot of copper in a lot of things, and 40 years is not that far in the future. 16 years for chromium. Get down here and you're looking at silver 21, gold 16, 10, 15. We use a lot of that stuff. And we're under 20 years on some of it. And again, that's going to change a little bit. It might get shorter too. It might be less. We don't know yet. But those are things that we need to start paying attention to. And that's the same what I just said a few minutes ago about our oil reserves. We're going to talk about that in our next chapter, so I don't want to get into too much. But again, a habit of humanity is is waiting until it's too late and you're like, oh crap, what are we going to do now? When we could be preparing for it now. So we need to start looking into ways that we can recycle, reuse, or find alternative ideas or processes to do these things. So recycling is kind of a loaded question, and I'm just going to share a little bit of my personal experience with you all right now and just tell you the nuts and bolts of this. The way humanity is we're going to do whatever's going to make the most money for whoever's in charge. That's basically what's going to happen in this world. I don't want to sound very pessimistic, but that's just the way the world works. And currently, recycling is not a big money maker, unfortunately. It's something that we should be doing. It's going to extend our resources tremendously. But some things we can't recycle. We just can't. But the things that we can, we don't do a very good job at it. We don't make it economical to do it. And that's what's really hurting that part of it. So let's go into environmental impacts and mitigation, some of the regulations. So the last two first, the Clean Air Act, Clean Water Act back in the 1970s, they really stepped up the environmental regulations on mining because essentially before those there were none at all. And those mines were just left, and anything before these two regulations came into effect, it didn't apply to them. So basically what you had throughout the history of the United States is people would get mines, they would mine them, they would destroy the environment, and then they would just walk away when they were done and leave the pollution there to contaminate the environment or for somebody else to clean up, namely the U.S. government. So when we get these two, the Clean Water and Clean Air Act in the 70s, it did help. There's a lot of argument in this country and politics today about regulations. Again, I'm going to go back to what I just said. My career started in the EPA back in the 1990s. I worked several years with EPA, and just to be quite blunt about it, businesses, industry do not care at all about the environment. Most of them, I can't say all, but most of them, it's what makes money. That's the bottom line. So if some way we could make cleaning the environment a way to be profitable as well, we would be golden. And that's what we need to try to get across to people. The General Mining Act, it mentioned here in 1872, this is an act that is absurd in today's world, but it was never taken out of law by Congress. And basically, back in 1872, the country was in a spot where they needed resources to build stuff. And of course, back then, again, not many people thought about the environment. So the General Mining Act of 1872 basically says that if you find some resources on government land in the western United States, you can then purchase that land for $5 an acre and you can mine it. They never took that law off the books. So you get up in the 1900s, you've got multi-million-dollar corporations that find some resource on federal land. Hey, we want to buy that for $5 an acre. So they pay nothing for it. The government gets nothing from it. They get no royalties or anything, no taxes, nothing. This company goes in there, makes their millions and billions of dollars, and leave. And leave the government to clean up all the mess. So you can kind of understand why we're in the situation we are environmentally with some of these things. It's a lot more complicated than politicians today want us to believe it is. The way that these things have been done, and it's really bad in some areas out there. These are some examples of heavy metals from acid drainage from mines. We've had several examples of this in the West recently, where abandoned mines started leaking or failed completely, and the water ran into rivers, basically destroying the rivers for miles and miles. You've got I've already mentioned the processing of ores is very, very hazardous to the environment. I mentioned the acid for the copper mines. Also, the smelting puts a lot of sulfates into the air. That's where we get acid rain. That's actually one of the bigger success stories with the EPA. When I was young and in college and studying, acid rain was a big deal across the country. The Northeast, the forests were dying from acid rain. The EPA put a lot of regulations on the stuff that came out of the stacks of these smelting places, and that's gotten a lot better in recent years. Some other things that you see here, you see this photo down here. It looks like sinkholes I showed you, right, in Kentucky. That's actually not. Those are mines that are collapsing from the mines are dug below and they're collapsing from the surface. So you've got subsidence going on there. We studied that. And then you've got your abandoned mine hazards, people going into these things and getting killed or hurt or whatever the case. This is quite a pretty good little system that they have set up on some of the mine drainage. Typically, you're going to see this on strip mines. I guess sometimes you might have an underground mine if it's in a mountainside, that you could do this on the side of a mountain. But basically, what you do is you have a series of wetlands and different filtration systems that gradually cleans that water as it runs off before it gets into the stream down here. And that's going over. I'm already way too long on this lecture, so I'm gonna let you read over this in your textbook. But it's a pretty good system to use on those sites. So that's it for this lecture. I'll get this up as soon as possible, and y'all keep up the good work. Thanks.